Today we're going to look at the applications of the sine and cosine functions. If you have your packet, these are the notes that you're going to want to use. If you don't have packets yet, you might want to just take notes on your own separate paper, and then you can either fill them in later or just scrap them. Let's start with the idea of complementary angles. When you have a right triangle, we know one of the angles is right. The other two, though, have to add up to 90 so that we can complete the triangle with our triangle angle sum theory. So therefore, those two remaining angles are complementary angles. These two angles are going to work hand in hand in the right triangle. We can perform any of the trig ratios on either of the two acute complementary angles. So they're going to be referred to as co-functions, and they do have a relationship with each other. Here's the official definition of cofunction. It is going to be a pair of functions that are going to be the same. Feel free to pause the video at any time if you need to stop and take notes. So let's look at an example. Sine of 80 degrees is going to be equal to the cosine of 10 degrees. You can see that the 80 degrees and the 10 degrees will add up to 90, which means they're complementary. If you want to grab your iPad, you can type in and find the decimal equivalent for sine of 80. Make sure you're in degree mode. And this is the value that should appear. You can also do that with cosine of 10 degrees. And you should see that the two measures are exactly the same. If we try two different acute angle measures, sine of 25 and cosine of 65, again, the 25 and the 65 add up to 90. So there's the decimal equivalent for sine of 25 and the equivalent for the cosine of 65. And again, they're exactly the same. Remember, though, we're working from two different angle measures, but they're going to provide the same result. In our last example, we have sine of 45 and cosine of 45. And same thing, if you type them into your calculator, there's the equivalent for sine of 45 and for cosine of 45. And these two are exactly the same, but this would also indicate that you have an isosceles right triangle. So because the two angles are complementary, we're always going to see this type of arrangement occur with our two complementary acute angles in our right triangle. So here's a generic value, sine of A, and A can represent any measure between 0 and 90, of course not inclusive, and then the cosine measure is the difference between 90 and the value of A. You can also switch it around and start with cosine, but sine and cosine, those two angles will add up to 90 degrees, and they should have the same decimal equivalent. So to refresh your memory, the sine ratio always uses the opposite side compared to the hypotenuse, so some old hobo. And the cosine ratio always uses the adjacent side to the hypotenuse, caught another hobo. And of course, we reviewed tangent before we left, and that one is you're tripping on acid. So let's start with our first example. We have Candace who's flying a kite. We want to draw a picture to model this so that we can get a good idea of where the label should go. So draw your right triangle. It says that the string makes an angle of 38 degrees with the ground. So as I add to my diagram, you can see I have Candace and she's flying her kite. The kite string is 300 feet. The kite does not go directly up. It kind of goes on an angle. So you can see that that is the hypotenuse or the diagonal of the triangle. And the string makes an angle of 38 degrees with the ground. This is our angle of elevation, and I have placed it down here where Candace is standing. We are looking for the height of the kite. So I've put an X right here. So if you compare that, if you're standing here at the 38-degree angle, we have opposite and hypotenuse, so that would imply a sine ratio. So as I set it up, there's sine of 38 degrees, x is my opposite, 300 is my hypotenuse. If you would like, you can put the sine of 38 over 1 to make a proportion. We're going to go ahead and cross multiply. So when I do that, I'm going to have sine of 38 times 300, and at this point it's just calculator work. Make sure you close the parenthesis after 38 so that it doesn't ruin your answer. This is the answer that should come up, and we want to round it to the nearest foot, so it does round off to 89 feet. Remember, if you want to try the examples before I reveal them, you can stop the video at any time. All right, let's try a new example. On to example 2, so we can again start by drawing our picture. We have a wire that reaches from the top of a pole to a stake in the ground. So assuming that the pole is perpendicular to the ground, I've labeled the pole here, and there's my right angle. The stake is over here in the ground, and it's 35 feet from the base of the pole. So if I continue to label, there's my stake, and this distance is 35 feet. So we know that the wire will make an angle of 65 degrees with the ground. I'll continue to label. There's the 65 degrees. This is angle of elevation. So we have Sam who wants to zip line down the wire to the ground. We need to find to the nearest foot the distance that Sam will travel on this wire. So there's my unknown x. And again, if I'm here at angle 65, 35 is my adjacent side, and x is my hypotenuse. So that means that I have the cosine ratio, adjacent over hypotenuse. And I'm going to go ahead and set that up. Again, if you want to put cosine of 65 over 1, you're welcome to do that. And then we're going to cross multiply. So this time, when we multiply cosine of 65, we're multiplying by x, and it's equal to 35. We're going to want to divide both sides by cosine of 65, and that should give us a correct answer. Make sure to close your parenthesis after the 65, and we should have 83 feet. Our last example is number 3. There's my diagram. We have a ladder that's 25 feet long. It leans against a building and reaches a point of 23.5 feet above the ground. Remember, the ladder cannot be up against the building or you will fall and crack your head open. So just know that the ladder is on the diagonal. That's my hypotenuse. Joe wants to climb down the ladder, but he refuses to traverse anything steeper than 75 degrees. So we want to find the angle that the ladder makes with the ground. So as I continue to label, I know that the ladder is 25 feet long, and that's what I have here on the hypotenuse. The ladder will reach a spot up on the building 23.5 feet tall. So the angle is missing, and I'm going to use theta as my variable. If you look at what we have in the diagram, from theta we have opposite and hypotenuse, which means I'm going to use the sine ratio. So this will be sine of theta. There's my opposite and my hypotenuse. When you're trying to find an angle measure, remember this is an inverse function. So we want to activate the inverse sign. Theta and the ratio switch sides, and then the rest is calculator work. And you can see that the angle will round off to 70 degrees. So can Joe use the ladder? Yes, he can. It's not as steep as the 75 degrees. If you have questions, send me an email. You can text me. I can also give you my home number. It's in a previous email, but it's 257-5113. That's my home line, and that one has better reception than my cell number. Please don't hesitate to call me if you need any help while you work on your homework. This is the homework that you should use. I sent it in an email. If you're waiting for paper copies, then you'll have it, and this is the one that you'll want to mark as number 101.